Hi everyone, this video is for number 14 from your review guide. So what we want to do here is we want to write an equation for the piecewise function that we have pictured over here on the left. And the hint that's provided in your guide is that the toolkit functions that were used in order to create this piecewise function have been transformed. In other words, they've been shifted or they've had some sort of stretching or compression that's happened to them, or even flipping. So I'm going to go ahead and take this piece by piece, and I'm actually going to put our piecewise function over here on the right. So I'm going to put my final answers over here when I'm done. So the first thing that I'm going to go ahead and note is I'm going to take a look at both of those pieces. So the purple, for example, I'm going to go ahead and define what the domain is for that one. In other words, what x values I am allowed to use here in order to create it. And as you can see, and I'm going to go ahead and highlight this in some color, our particular function that we're looking at in purple, it has a closed dot right at x is equal to -3, and it has an open dot at x is equal to 1. So in this case, my domain here is going to be my x here, and it's going to be between -3 and +1. So what I also want you to note is my choice of inequalities that I used here. Notice that I have -3 is less than or equal to x here, and that is because I do have a closed circle represented over here. I'm going to try to thicken it up if you can kind of see that animation that's happening. To finish off that description for the domain, I also have x is less than 1. So notice in this case I do not include an equal sign as an option here, because when I'm graphing this, I have an open circle that is happening here. All right, so what I'm also going to do is I'm going to identify the domain for the piece of the function that I have in red. Again, if you kind of note here, it looks like I have an x value that starts at 1, and what I also want to note here is that this particular function continues on indefinitely. So I didn't have any sort of closed circle or open circle on the image. So that must mean that this is going to continue to basically extend out, and it's going to slowly but ever so slightly push out as I keep going. So I will eventually start using all those x values that are going off towards the right. In other words, I'm going to use values from 1 to +infinity. And how we would describe that is we would say, well, x is greater than or equal to 1. Again, I'm using greater than or equal here because I am using a closed circle at this point. All right, so let's go ahead and actually find out what those pieces are called, or actually what those pieces to the piecewise are. So again, I'm going to focus on the function that I have in purple first. So what I want to note here is that I'm going to start off with, this looks like a square root function. So in other words, I'm going to have something that looks like y is equal to the square root of x. But I need to go ahead and actually start adding components in here because there's a lot more that's happening than just a square root of x function. One thing that I want to note is I'm going to focus on where my square root function begins. So where that open circle is. If you recall from your toolkit function, your square root function usually starts at the origin. So since we know where the starting point of a square root function usually begins, we can actually denote what the horizontal and vertical shifts are. In this case, it looks like I traveled to the right 1, and then I traveled up 1. So I'm going to go ahead and make a note here that says that this is going to go to the right 1. So I'm going to go ahead and extend this out and put a -1. If you recall, we have the house of lies, so we're actually going to put the opposite of what we see when we are creating this function. And on the outside, I'm going to put a +1 to indicate that vertical shift of 1. Another thing that we can note is that usually our square root functions, if I were to draw like the traditional parent function here, it not only does it spring from the origin, but it also goes to the right. So it stays in that first quadrant. If you notice, in this particular case, mine is not only is it not going to the right, but it's springing off to the left and continuing into the second quadrant. So what I want to do here is I want to note that I must be doing some sort of reflection. And in this case, notice I'm reflecting across the y-axis, or in other words, what I'm doing is I'm changing all of my x value signs. I'm swapping them. So that means that I'm doing a horizontal reflection. And what I want to note here is that I am putting that radicand of x minus 1 inside parentheses. If you recall from class, we had talked about the general presentation of a transformed function. I'm going to go ahead and write it above my graphical image. We had said that that was y is equal to a, which represented my vertical or horizontal shift, times the function, we'll just call that f just to represent any of the toolkit functions that we're studying. And inside there, it's going to be your horizontal stretch or compression times x minus whatever your horizontal shift is. And then outside, we're going to do plus k, so whether we move it up or down. So we do want to put parentheses around that expression of x minus 1. And then denote what kind of reflection we have happening here. So since we are reflecting across the y-axis, or in other words, we are doing a horizontal reflection, we are going to put a negative there. So we don't necessarily want to leave it like this, but what I am going to do is I'm going to clean up some of my images here so we're not overwhelmed with what we're looking at here. So, bear with me, everyone, sorry. Okay, let me put that dot back where it was. Okay, so now I'm back. All right, so the other thing that we want to note here is that, well, is there a potential vertical stretch or compression? In other words, and I'm going to denote this in green, do I have something that I'm multiplying by out in the front? Remember, whenever we were constructing functions from graphs, we didn't worry about actually finding what b was. I had said that that was too hard to do, so we're just going to focus on a. And what I would recommend doing is finding an easy point that you can work with here to help you out. Okay, so I actually am given a nice one to work with. I am going to work with my endpoint here. So I'm going to work with point -3, 5. And what I'm going to do then, let me clear this out so I have some room. What I'm going to go ahead and do is I'm going to go ahead and drop those values in. I know y is equivalent to 5. I am solving for a. And then I'm going to move into the function, and I know that x in this case is going to be -3. And by doing this, if you notice, since I filled in the positions for x and y, a is the only variable in this case that I can solve for, and that's actually what I'm looking for. So we'll go ahead and we'll clean this up. So 5 is now equal to a times the square root of -3 minus 1 is going to give you -4 plus 1 on the outside. And as I continue, I'll clean up the radicand. This is going to end up being a +4, because a -4 becomes positive, plus 1 on the outside. 5 is equal to a times 2 plus 1. I'm going to go ahead and subtract that 1 because I can easily remove it. and this is going to give me 4 is equal to a times 2. I will divide both sides by 2, and I find out that a, in this case, is 2, because 4 divided by 2 is 2. So now what I can go ahead and do is I can change out what I have up here, right underneath the image here. Okay, so I'm going to come in and I'm going to erase out the a, because now I know that a, in this case, is 2. So the first part of my function here is going to be 2 square root negative quantity x minus 1, and then plus 1 on the outside. Okay, so I need a little bit more spacing, so I'm going to go ahead and clean that up a little bit. I'm going to move my domain, essentially, so it doesn't look like it's all running together. So I'm going to put negative 3 less than or equal to x less than 1. So this is my first piece. So now I'm going to turn my attention over to the piece of the function that I have in red. And if you notice, the shape that it has, it kind of looks like a cubing function. So what I'm going to start off with in this case is y is equal to the cube root of x. Or, yeah, sorry, not the cube root of x, the cube of x cubed. So from here, what I want to note is the point of inflection. So that's going to be where our image kind of twisted. So it looks like that twisting happened at point 2, 2. So that, again, is going to help us out, because, again, if we were to look at a general sketch of a function, we can note that for a cubing function, that point of inflection usually happens at the origin. So how did that point of inflection get moved? If we move 2 to the right and then up 2, then that actually indicates what has happened. So I'm going to adjust my parent function here. So I'm going to remove the cube for a second here. And I'm going to say, all right, I know that I'm going to the right 2, so I'm going to do minus 2 on the inside, put that cube back. So my change, that was my horizontal change, so what happened inside of the house, and remember I did the house of lies. And since I went up 2, I'm going to add 2 on the outside. What I also want you to note here is take a look at that general sketch. Look at how that cubing function is oriented. It starts off in the 3rd quadrant and finishes in the 1st. In my case, if I were to move this point of inflection here back to the origin, it did the opposite. It starts in the 4th and ends in the 2nd quadrant. So that must mean that I did another reflection. So given the fact that this is a cubing function, you can kind of identify that reflection as either vertical or horizontal. So if you were to, for example, take a moment and, take this edge here and move it down, you'd see that you would get that where the function exists in the 2nd and 4th quadrant. If, again, you were to take this end and flip it, you would also see that you would be moving it so that the function now is occupied in the 2nd and 4th quadrant. So I'm just going to go ahead and say, I'm going to call it a vertical change, or a vertical flip, so I'm going to put a negative out in front. And my main issue here is that, well, I need to take into account that there might be some sort of vertical stretch or compression. Again, remember, we are not actively going to be looking for any horizontal stretches or compressions. We're just going to focus on the vertical ones, because most likely we can take a vertical stretcher or a horizontal stretch or compression and make it vertical. So again, I would go ahead and suggest picking an easy point to work with. I would say let's pick that point that ended. So I'm going to work with point 1, 3, and we'll go ahead and we will check. So I know that 3 will represent y. We have a negative, and I'm going to go ahead and drop in my 1 for my x value. And then, oops, sorry, that did not work out the way that I wanted it to. Sorry about that. That's not where that should go. We should have a here, because that's what we are looking for. I apologize. We would come into the quantity. We would put 1 in for x, and then do minus 2 cubed plus 2. And as you can see, then the only variable that we have left is the a. So we're going to go ahead and solve for this. So this gives us 3 is equal to negative a times 1 minus 2, which is negative 1 cubed plus 2. Then we have 3 is equal to negative a times the negative 1, because negative 1 cubed results in a negative 1, plus 2. We can go ahead and clean up what we're seeing here, since we have negative a times negative 1. This would result in 3 is equal to, a negative times a negative is positive, and a times 1 is just going to be a. We'll subtract 2 from both sides. And actually what we're going to find out here is that a is equal to 1. So we didn't actually do any sort of stretch or compression here. We left that part alone. So really, if you wanted to, you could either just not write anything in for a, so you could just kind of come in here and take the a out, or what you could do is you could put 1 in its place. They're saying the same thing, it's conveying the same amount of information, you are just, in this instance, revealing a little bit more in terms of the detail. So again, I'm going to go ahead and move my domain over a little bit so it doesn't look so crowded. I'll put my x is greater than or equal to 1 here, and I'm just going to write out my solution as the final piece. So this is going to be negative quantity x minus 2 cubed plus 2. And what I'm boxing is your final solution. I might just finish it off and like put in f of x is equal to here so that I have the appropriate function notation. Other than that, I'm all done. I've established the domains that I'm underlining in yellow, and then I've identified the pieces that I'm underlining in green. So there you have it. If you do have any other questions, please let me know.